is introduced by Hoffman and invented by Zeta, which is a real number defined by the following infinite sum. One over n1 to the k1 and mn to n, where m1 and m1 are the integer satisfy this inequality. Is the real number, where k is some sequence, finite sequence of integers, which are non-negative and positive. And the first one is strictly logical language. And this k is called an index, which k1 strictly logical 1 is called an index, an admissible index. And if we drop this condition, then it is called just an index. And we denote by the absolute value of k to be the sum of entries, and which is called the weight of the index, and also the depth is equal. We define the depth of the index to be n, and there is a p-adic version of these multiple zeta values, which was first introduced by Caruso and Navarrete, and now he was in Kyoto. And where p is a prime number. We will go this definition later, but it is the p-adic multiple zeta values, but denoted by this of p of k, which is p-adic numbers. Okay, that's what it is. In the paper where p-adic multiple zeta values are introduced, Caruso asks that the following question. He asks that this is belongs to the ring of integers of Kp, and my first main theorem in this talk is that for any admissible or index of weight k, then this multiple p-adic multiple zeta values belongs to the case p-adic or p-zeta, which is by definition the idea of the p generated by the divided power of p. Okay, where we have p in particular, it is a psychological P. So this is our affirmative answer to the question of Caruso. And in my talk, I would also like to explain some application to the theory of finite multiple zeta values. So we need to introduce some more notation to explain the result. First, we introduce the multiple zeta values. If it was studied by set the whole line and so let K be an index. Then multiply multiple zeta values in the finite side. So and this is a rational number, but we regard it as an element of the finite field. And multiple zeta values introduced by Kaneko. Is defined to be a system of these multiple zeta values. This regard as an element of the some ring denoted by A, this is by definition that is the product of the finite field E tensor B here. And this was denoted by Z sub A K, where K is a non-negative integer, is a Q vector. This is the Q algebra, so we can consider the Q linear subspace generated by these finite multiple zeta values of weight K. Then the Gauss sum with respect to K of this space or integrated Q algebra. And it is conjectured by Kaneko and Sagino. It's that the dimension of each sub k is equal to k minus d sub minus 2, where dk is a negative integers defined by the following generating function. So in particular, it is equal to k minus 3 is strictly positive. So our main result is that we have an inequality in the relation of this equality. The k is at worst expected and then the next section, in section 2, I will give an outline of proof of the first theorem. But to go into the details of the proof, we first recall the definition of p-adic multiple zeta values. Let K be an index let V sub K of T is the following form of series. The summation, the range of summation is the same as the multiple zeta value. And the denominator is also equal to the same. But the numerator is T and 1. This is the power series with coefficient the rational number. And this is called the multiple comparison. If K is admissible, so K1 is strictly larger than 1, then the value of the multiple point logarithm at 1 converges to a multiple zeta values in order. However, the p-adic topology, this function and converges on where the p-adic absolute value is strictly smaller than 1, but it is divergent, not convergent to 1. So this is the bad news, but however, we can make some analytic combination via Coleman's theory of p-adic integration. And by using this theory, we can find the p-adic multiple zeta values. With our diagram denotes the ring of form our series, which is over-convergent in the sense that it is convergent on P strictly larger than, strictly smaller than epsilon for some epsilon, which is strictly larger than 1. But in my explanation, we can take epsilon to E, which is the P to the minus 3. We can take epsilon to this number. But anyway, for any two index indices, K and K5, such that their weight of K is strictly larger than that of K5, there exists a unique element with K and K5. Which belongs to this ring, such that the multiple logarithm. But substitute the variable p by with p to the p over p to the p minus p minus 1 to the p. This is equal to the p to the rate of k times the original multiple logarithm plus some other terms where in the sum k prime runs over its own indices whose weight is strictly smaller than that of k. And h k prime times the multiple logarithm. Yes. One can compute this function h, so k prime, by explicitly by using some partial integration.
Is it for convergent?
It holds on.
Yes, so
Okay.
François, on peut mettre le micro? Oui.
And what can we find?
A question from Paris. So, yeah.
So I have a question on your formulas. So one question is whether the empty index is allowed in some formulas, and another question is
Empty index is allowed. Yeah.
yeah. So then the
We allow
value,
empty.
and so there are conventions to define things for okay, and
Yes.
so the empty index is considered as admissible as okay.
Yes, admissible.
Admissible. So and then
Yes.
H k prime lies in which is what kind of thing? Is it in the ring R dagger or where is it?
Yes.
Ah, okay.
Okay?
Okay.
Okay. And then we can define the p-adic multiplication value. Inductively, as a formula, so the value that the empty index is equal to 1. And the other case is equal to the p to the k and p of k and plus we can evaluate the function which is this convergence values is nice convergence property, so we can evaluate it as t is equal to 1 and then t. Then I will give approval to, I will try to prove 7.1. In the rough structure as follows. In the definition in the previous section, we use something like a rigid interpretation to define rigid cohomology to define p-adic multiplication value. But it had a bad interpretation. So in this section we use alternative definition by using threshold interpretation. In our case, we have a good integral structure. So let x denotes a p1 over zeta. and with straight sections 0, denoted by 0, 1, infinity, each of which is isomorphic to the CP, and we regard the sum of these 3 points as a normal crossing divisor, and regard this as a low racing scheme associated to the normal crossing divisor. Then we have an obvious equality, and X is the union of X minus P, which is an open subscheme, where P runs over the subset of 3 points, which means that the subset of P, non-empty subset, of the set of 3 elements, and here we regard this as a closed subscheme of X corresponding to P. But anyway, this defines a final covering of the underlying scheme of X. This covering really goes by U. For any integer k, which is non-negative, by taking direct product, we obtain UK is something like a direct product of the covering. So then which is an affine of the covering. The K for tensor product, final product of X over CP. And for any element of these 3, the set or the final set, the affine scheme X minus I has it makes a canonical list of problems. For example, if I is equal to 1, then P1 minus 1 has a canonical limit which maps P to P. This is very compatible with the log structure. And by symmetry, for any other I, we have similar canonical list properties. And for any non-active finite subset of these 3 points, by rolling up, if necessary, of the final product, it's my I, where I runs of the element.
You mean if I is different?
And then by removing some stretch transform of some divisors
I know it's a trivial.
of the final product, then we obtain some exact cross conversion from X minus P to Z minus P. And similarly, we have exact cross conversion from U to the Z denoted U
グラフ where? どこでグラフするんですか？
Here, grow up with some, yes, something like a, yes, this grow up is necessary only when the cardinality of p is equal to 2, and is something like exactly something. This grow up with this point of the coordinate of 2, and and remaining this, and we obtain ZT. But anyway, if we obtain a canonical exact first inversion, and this scheme has a canonical and we do not find for any u is element number of average. Okay? And let dum denotes the PDM plus. I will disclose the version of PDM. And omega dot u and the product u dm also the logarithm the complex. This is u and more again. Then, but everything is in affine. Yes, we know that these schemes are affine schemes, so we can regard these complex just as a complex of ZT modules. And then by passing the projection limit of un when u varies, and we obtain the ZT modules. The crystalline topology, log crystalline topology of P1 is log structure 3 point over and also the canonical vector properties define the natural action of Frobenius action as a complex. So we can recover the complex properties in the logarithm using this complex. Why? Y is a special fiber. Y. And then we can define the map or complex from C sub k to C sub k and 1, which is defined to the integrating sum of another you have to define sub I, where the sub I is defined in the product to the some variable I plus 1. This is the coordinate of the r's component, r's factor of the x to the I of 1 to I. Except for the h, where I run over the 0, k, and f0. F0 is a raptor. Meaning of f0 is a pullback to t1 is equal to 1 part t1 and 1 that and f k is a rapid taking the pullback to k equal to 0. Yeah. But in this case, we can this embedding does not induce a dipole conference or this modulating force. So we define we have to define the morphism or conference explicitly by forcing the et. For example, in this case, et equals to 1 down to 0. Then we obtain a double complex. And then take a total complex and take the zeros cohomology group. Where the degree 0 part of C0 is placed at degree 0. Then we denote it by h. Then one can show by using the Gaussian freeness of crystalline cohomology in this space that this is Gaussian free, or more precisely free zeta motion, and which admits a canonical base index which we denote by e to w, where w is a set of words, the free moment, ferromagnetic moment, generated by two elements, A and E. And this H also has an additional structure.
Excuse me, this is
done by hot field operation and also wave field operation. And satisfying the pretty sounds like mixed state.
So question from Dennis?
yeah, I'm not sure about the question, but so this is infinite dimensional, is it?
Yes.
And each of the C dot is as finite dimensional cohomology?
Yes.
And so when you take the total complex, is it a total complex where it's infinite, that is that you have to take infinite direct sum or infinite direct product? Or
Yeah, direct sum.
infinite direct sum?
Yes.
Okay. Okay, I understand what you're doing. Okay.
And also the credit issues with respect to wave filtration is equal to 0 where the index is odd, and And when it is even, the probability is displayed explicit by these numbers. So this implies that there exists unique, also the dimensional, one-dimensional, and this is the root zero is one-dimensional, root zero. Generated by the image of the eta of empty. Okay. So this implies that there is this unique linear map from H to QP such that satisfy the following properties. The first one, this map is like to denote by zeta. So the zeta is a probability together. And the second property is that the image of zeta of the element eta sub empty is equal to 1. And key observation is as follows. The first is the term K index. Then Venus light W of K for the monoid element of the monoid. You find as follows. A to K minus K1 minus 1 would be and K2 and so on. Then the image of the map zeta of the element eta sub WK is equal to the minus 1 to the depth of K times EF minus zeta value. And the second observation is that the image of phi of the QK, we can define the hot filtration at the compressed level in some standard way. And I should do this. This total convert by C. The image under the properties of the case hot filtration is contained in the case divided power times and your times risk complex. And by using these two observations, we obtain the first one. The third question I would like to give outline of the waveform. To explain this, we need to introduce another version of p-adic multiple zeta values introduced by the This denoted by QP double bracket value to form a completion. Monoid algebra. And have a natural structure of some completed proper everything. And first, multiplication is the usual multiplication, and home multiplication is given by 1 tensor W plus W tensor Y, where W is in or D.
I don't see the.
Ça va venir. Si quelqu'un coupe toutes les 20 minutes.
Pourquoi?
C'est ce que vous devinez.
And we define phi of kz. And this is some case Frankfurt associated referring to the p-adic equation. The image of zeta and the zeta of the ether sub W will W. Then it is group like. Okay. And by definition, its coefficient is equal to is described by p-adic multiplied with the values. Now we define
Vamos comentar uma palavra aqui. Formar condição.
yes, no commuted two variables. And we define the Green's version of the associated. This is also an element. By the following relations. So, cycling and circuit. Times and the usual KC. But then we substitute the variables A and B with A over P and B over P and taking conjugates by this one. Is equal to this characterization is unique to characterization. And we define the domains values, multiple intervals, to be the coefficient for the W series KW and W K. So the word, the element of unknown corresponding to the index and times corresponding to the also denote by W as a minus 1. So therefore W is the number of the letters being appearing in the element. And the key formula is the formula. Which I once called the conjecture tool in some conference, which is last August. It said the rings p-adic about downward project to the sum of minus p to the L times the p-adic of the integralities without k, but we have some integral at the end. Then our condition to what as follows: for any index k, we have an equality minus 1 to the k1 to ki, and the downward version of ki to kn, and times the usual version of ki plus 1 to kn is equal to the k, which is the final sum. It is the same expression as the mod p not to the points, but we regard it not under element of finite field, but as a rational number. And this is called the finite multiple harmonic sum. This is the conjecture second to what we call conjecture 2 last year, but yeah, it is already proved by p-adic, I would say. And you can to be more precise, it's the special case. And p gives a self-contained is good. Or one of his theorem.
Hello. Question from Paris?
Just the convention on the indices. That so you had in the beginning the condition that K1 is big, at least 2, it's called admissible. But then here we don't have this condition, or what?
In this case, this assumption is unnecessary.
So all the definitions of the p-adic things are without this assumption, or only this?
Yeah.
All the definitions are without this. Okay. In the p-adic.
But
Yes,
in the whole p-adic story, you don't assume any admissibility of the index, or just here?
Yes. No, we don't assume.
Okay.
Yeah. Yes.
Japanese yes.
Yes. I would like to give a sketch on the proof of this proposition. This is his proof. We need to introduce some more notation with the Z0 is a solution. And KZ is a solution. Yes, which is introduced, I guess first introduced by Professor, and this is some form of power series. Also with a form of power series with coefficient in some ring as Coleman, which is called Coleman function. But we only need to use some power series expression, so we only need regard it as some subring of the power series times and the former power series and polynomial over log p. And this was improved by, and also the coefficient. One corresponding to the index is equal to the multiple polar over 2. So log part doesn't appear in the after sign. And but in fact, this is multiplied by these properties and the coefficient of and some weak conditions. But and also there is some over-conversion variant. Yes. But I would like to make this distinction, but because it needs to introduce some more notation, and it is also verified. And also, so we can evaluate it as t is equal to 1, but it is equal to the in much less the values. But the important is the following properties. This data version times g0 of p times the degree associator times d of p times d is equal to 0. All of the story in this blackboard is due to Bruce. Then
So this is a product or a composition? Or
Product.
product, okay.
Then that prime is also subset of W, which is equal to the empty word or the one which ends with E. So this corresponding to the one corresponding to the index. And we have obvious now for dropping some coefficient, dropping some terms which is not belongs to double prime, which we will have the illustration to that, the symbol illustration to double prime. And take this operator and then to take the coefficient. Then it is the both side becomes a formula for the solution. It doesn't appear the term of log polynomial log. Then consider the coefficient of p to the k. Then obtain substituting to subtract time. It's equal to 0. And we obtain this formula. And let's consider the operator A inverse. What is the operator obtained by dropping A, the letter A in the leftmost side, which stands for AW, the word A up to W, and the other ones to 0. We apply the operator P times the inverse to the equation. Then key point is that P and A inverse to the R of the first term is conversion to 0, makes sense? But the other one, the last term is stable under this operation. And this coefficient is, we can describe using the multiple harmony sums. And also the second term is easy because the coefficient of the between 1 is equal to just yeah. By using this reaction, and then the remaining time, in the remaining time I will complete the theorem, which follows from some following then H is something like an there is a written coordinate of something like in some integral some subring of the pi1 fit to the round torus of mixed space in capital mixed space model. This is complex information. Yeah. The equation to the realization function, getting around the realization function. Of the realization function to some first aspect of the way, which the calculating which the values. when the subscript, this subscript means it filtered on the form to satisfy these conditions. We look at H bar, the quotient of H by the ideal generated by the monotypic zeta 2. And this has a natural structure of a gradient algebra. Also, H has a structure of gradient algebra, and its dimension is equal to the design of everything. And we have a p-adic comparison formula, which is based on the work of Yamashita. But anyway, we obtain them. If we fix something here, then we have a map from H to B around. But the image transfers through B. When B is the Dallas sum of BK, and BK is the intersection of the probably B crease and field 0 B off, and then taking phi is equal to E to the K part. So we obtain the map. But this is not the graded homomorphism. And this implicit map of H bar is the quotient of B over the ideal generated by element usually denoted by P. And this doesn't depend on the choice of the embeddings. We can put projection to the big just P part, so we have bird. And by using this, we obtain a map of C of finite Adele from H bar to the zeroth sum, rather equivalent to P, which stands an element in degree K to the collection of its image under C P bird divided by some power of P. Then the consequence of theorem 1 has some result of Brown. Its image CAF is contained in the subgrid of finite Adele. And another consequence of theorem 1 and the proposition above implies that the property divided by C and above A, which is H bar of H. Which is the outside book. I have not explained it yet, but it has a natural structure of top of zero, so we have another outside book. And there is a natural projection from finite Adele to A, or A. Since the symmetric version of the motific multiple zeta values. The finite multiple zeta values. So in particular, VAK is containing the image of CA bar with respect to the root profile. So we have to just zero.
Also, I guess being in this formula, there being zeta or motivic zeta.
Motific zeta.
Motivic zeta.
Yeah, but we can approximate. Yes, but we can approximate the range zeta by the user zeta. So yeah, this kind. Yeah. Oh. If P is sufficiently large for fixed index, then the least multiple zeta is nearly equal to the antipoding version of the PM multiple zeta divided by its rate. The P to the square. And also, finally, I would like to remark that this, in some argument, we can show that this equality point in this inclusion. So we obtain the map from the exponents the value sum of the here. And also we obtain the two surjections, and it is an open question then, and also it is conjectured by, in some sense, by an echo to Z A. Question is that it is expected that these two surjections is an isomorphism. Okay. Thank you very much. Thank you very much. There are any questions from Paris?
Okay, so any questions from Paris?
So the relation. So can you explain the relation of you define certain expressions using truncations in the definition of you defined p-adic multiple zeta values, but also you define those in the Kaneko-Zagier for so there were finite sums in F. I don't find it in my this one. Yes, so can you explain the relation between the finite sum and the multiple zeta? So, do you?
This one? You mean this one? This is the finite sum, so we can consider it's a P version of this, then we obtain something like this.
Consider what?
This is the finite sum.
Okay.
It is the finite sum, and the enclosure P is equal to the mod P multiple zeta values, and it's called, and it is a member of finite multiple zeta values. And I'm sorry, this is missing, but this is the limit p-adic multiple zeta values, but it is related because of definition to the antipoding version of the p-adic multiple zeta values. So by using this formula, we can relate the finite sum and some reduction of the the limits out with zeta values. So as a corollary of yes, so first theorem and combined with the proposition will be implies that if the rate of k is smaller, strictly smaller than -1, then n then no download version, just like this one. All stuff appearing in this finite sum is a p-adic integer in this case, and it must be equal to the final. By using this, we can relate some other values. And also, I have not explained that also the image of the motific multiple zeta values is equal to the p-adic multiple zeta values.
Thank you. Other questions in Paris?
So you also said that some map was not a graded map in the blackboard up there, and H was graded, I suppose.
H?
So the map from H to B is not graded.
So grade not to grade it.
So what does it?
So we don't go about the stop.
What does it do exactly?
This one?
Yes.
Yes. This is not graded. Yeah.
And does it send
yes.
estimates to?
These two have some grading. This has grading which follows the definition, and this also has a natural grading.
Is your question?
Yeah, I don't. So every element goes to a finite combination of things, so every element goes to a finite sum, or
Yes, finite sum.
okay.
Yes.
Okay.
Okay. So, are there other questions? David? No? Okay, so I think that's all from Paris.
Okay, any questions or comments from Reggie?
Any questions? I wonder if there's any relationship between the real zeta, Martin zeta value with the motivic zeta value.
Oh yes, there is another comparison, usual comparison map from H. There is a map from H to R by using the Bechthian drum, by using the Bechthian drum comparison point, and which maps to the motivic multi-dimensional values.
And do your results have implications for real Martin zeta values?
Oh yes, in principle by using this homomorphism, it is proved that the space of multiple zeta values of fixed weight is bounded by the dimension d of k.
なんか安田さんのこの結果でなんかリアルな感じでなんか。
Oh no. My result is only p-adic or finite logic. Yeah.
Oh.
Our result doesn't imply anything at real multiple zeta values.
There are no more questions from Beijing.
So at the end of the proof of theorem 1, you mentioned two key observations. So the second observation says that you have control over the properties. So this is something standard?
Yes, yes. This is due to simply nature of progress and relation of properties and concentration.
Okay. Thank you.
Any other questions? Okay, let's start the speaker.